Hello guys, and welcome to another calculus video. In this video we are going to be covering first of all, this is contour integration tutorial 3 out of 4. This is where we're going to get into the real nitty-gritty of evaluating contours that are in the complex plane. So in this video we're covering the estimation lemma, Jordan's lemma, parametrization for straight line and circular integrals, small circular calculations, and we're going to dip our toes into branch points and cuts, but we're not going to completely cover those topics. We're going to leave a little bit of that for the next video because it'll make more sense in the next video. So first off, let's talk about what's the point of stuff that we're doing in this video, because there's a lot of different topics that we're covering, right? So what more could we need? We already know how to evaluate contour integrals. So the issue is, let's say I wanted to evaluate the integral from negative infinity to infinity of f of x dx. I'm going to use a contour integral of f of z dz, and this is the path that I'm going to use. Now notice this real axis integral becomes, as r goes to infinity, our integral from negative infinity to infinity. But our contour has another segment, which is this large semicircle that goes from positive r looping back through the complex plane to negative r. So we could write our contour integral as I, right, this integral right here on the real axis, plus this gamma integral. This is a capital gamma, which represents this curve, this upper circular curve, so plus the integral over gamma of f of z dz, and this is equal to the overall contour integral, which is just 2 pi I times the sum of the residues. So if we want to actually get the value of I, we can't just use a contour integral. We also have to be able to evaluate this upper semicircle, which is what closes the contour. So that's what we're going to be covering in this video, how to evaluate these curves and others, basically any curve or even straight lines in many cases that we use to close our contours. We need to be able to evaluate those in order to evaluate our original integral. So let's go ahead and jump right into the estimation lemma. So the estimation lemma is very straightforward and pretty logical. So it just says that the absolute value or modulus of the integral over some curve gamma, f of z dz, is less than or equal to m times L. Now m is just the maximum of the modulus of f of z, where z is some point on that curve gamma, right? And then L is just the length of the curve gamma. So overall, we just end up with, the maximum value times the length, right? Which, just some basic reasoning, you can pretty much see that's going to end up being less, or that's going to end up being greater than the absolute value of the integral, or equal to it, right? And then we're also going to be using the triangle inequality quite a bit. This is just something to keep in mind. For two complex numbers, a and b, the modulus of a minus the modulus of b is less than or equal to the modulus of a plus b is less than or equal to the modulus of a plus the modulus of b. And that's very important. So let's just go straight into a worked example, because I think that's the best way to show how to do this. So for our example, we're looking at the function f of z equals 1 over z squared plus 1, and we're trying to show that the integral over gamma of f of z dz, again, gamma is this same curve. I'll always pretty much use gamma just to represent this big semicircle that goes from plus r to minus r in the upper half plane of the complex plane. Again, r goes to infinity. We're trying to show that this goes to 0. So the first thing we're going to do is say that when z is some point on gamma, z can be represented by r times e to the I theta, where 0 is less than or equal to theta is less than or equal to pi. So that just is saying that, that sums up all the possible values of z. So that means that our m is going to be the absolute value of 1 over r squared e to the 2I theta plus 1. Take the modulus of all of that, right? And again, we don't know the exact value of theta here because we're talking about the maximum possible value of f of z over this point. So theta could be really any value in between 0 and pi. So take the modulus on the top and bottom, and then using the triangle inequality from before, we know that the modulus of r squared e to the 2I theta plus 1 is greater than or equal to the modulus of r squared e to the 2I theta minus 1, and the modulus of r squared e to the 2I theta is just r squared, right? Because e to the 2I theta is just some angle that we're multiplying by. And so since this is greater than this, we take the reciprocals and the less than or equal to sign flips, so we get 1 over the modulus of r squared e to the 2I theta plus 1 is less than or equal to 1 over r squared minus 1, right? Then we multiply by L. Remember this was M. So I say ML here is equal to this, but really I just less than or equal to, right? So ML is going to be less than or equal to pi r over r squared minus 1. Now the length of this curve gamma, since it's just a semicircle, is going to be pi times the radius, and the radius is r, so that's where we get that. And then remembering that r tends to infinity, we know that this is just equal to 0. So if we know that the ML is less than or equal to 0, we also know that the absolute value, or the modulus, of the integral over gamma is less than or equal to 0. Now, since we're taking the modulus, we know that it's greater than or equal to 0, and it's also less than or equal to 0, so it just has to be 0. And in general, whenever we're picking a contour to do contour integration, we want the integral over gamma to go to 0. So almost every case that you're going to look at, the integral over gamma is going to be 0, uppercase gamma. So let's look at some shortcuts for this. When I actually do contour integrals, I typically will not write out that whole long proof that proves that the value of the integral over gamma is going to be 0. Usually I'll just kind of look at the order and make a little estimation, and I'll say, okay, I've convinced myself that it's going to go to 0, I don't need to prove it to anyone else. And that's something you'll probably see in engineering. So if you're into pure math and stuff like that, I would not suggest doing this, but if you're just trying to solve problems for yourself, I would suggest doing this. So if f of z is some polynomial p of z over q of z, some rational function, then as r goes to infinity, the value of f of z is going to essentially be on the order of r to the degree of p minus the degree of q, right? So that means our m value is going to be on the order of r to the degree of p minus the degree of q. And when we multiply by L is just going to be pi times r, right? So it's going to be, we're just adding one order of r, so just adding one order of r, right? And so that means if the degree of q is more than 1 greater than the degree of p, we can pretty safely argue that ml is going to go to 0, and that means the integral over gamma is also going to go to 0. And that's without doing any real math, just sort of adding up the order of things. And you can also analyze asymptotic behavior for other functions, like for example ln z. Really, as r goes to infinity, ln z is going to go to ln r plus some, I times some angle, but really that's not significant because r is so great. And then when we multiply by ml in this situation, ln z over z squared plus 1, it's also going to go to 0. So let's go ahead and try some practice problems. Keep in mind that the triangle inequality here can be extended to higher numbers. So for example, modulus of a minus modulus of b minus modulus of c is less than or equal to the modulus of a plus b plus c. So here are some practice examples. Go ahead and try these problems. Number 6 is a little bit difficult, so don't worry if you can't figure it out. So go ahead and try these problems. Alright, so hopefully you were able to figure out those problems. If not, you can always ask me about them in my Discord. So yeah, let's go ahead and move on to the next topic for today. Alright, so our next topic here is Jordan's lemma, and this is basically just a sort of truncated, more simple version of the estimation lemma for specific functions. So if gamma is the semicircular arc from plus r to minus r in the upper half plane, now note that this actually doesn't depend on the value of r. So this can be used if you have a smaller semicircle that isn't infinitely large, also to bound your integral. So this tells us that the integral over gamma of e to the iaz, where a is greater than 0, times f of z dz, is less than or equal to pi over a times the maximum value of f of z, the modulus of f of z as z varies along gamma. I don't even really have much practice for this, or an example for this, because it's really just straightforward. You do the same thing as before, you find the maximum of the absolute value, and you just, that's it. So it's much easier than the estimation lemma. So I have a few practice problems for this, but in general, if you don't want to learn Jordan's lemma, I'm pretty sure you can also, for almost every example, you can also use, estimation lemma. Except for this one right here, you wouldn't be able to use the estimation lemma. But so here are 3 examples, and show that the following integrals go to 0. For natural log of z, don't worry about its lack of analyticity. Don't worry about the fact that it's not analytic at some points, because that's just worry about the actual convergence of the integral here. So show that the following integrals go to 0. Alright, so parametrization. So this is a very, very important topic. And this is used also to how to do this to also evaluate, to make the estimation lemma a little bit easier. So sometimes some sections of our contours are straight lines that can be described in terms of normal integrals. And you can also do this parametrization with like circular arcs and stuff, but the main use of parametrization that you really have to learn is for straight lines. So if an integral is in a straight line, so for example, like if you have 2 points in the complex plane and our contour connects those in a straight line, then this is definitely the method you're going to want to use. So you're going to write it, it says write it in as the bounds. That just means write the starting point as a lower bound and the ending point as an upper bound. And then find a substitution z equals z0 plus w times x, w is some complex number, to connect the points, and then evaluate the resulting integral or combine it with other results. So this doesn't necessarily need to be the form of the substitution, but I'll show you some examples and really the significance of the substitution here. So let's go ahead and go straight into an example right here. So we have our f of z is 1 over z cubed plus 1. Our curve, lowercase gamma in this case, is the line running from z equals 0 to z equals e to the 2 pi I over 3 times r. So really this line should be a little bit more to the right there, but it doesn't really matter. And again, r is going to infinity. So notice that this integral is a straight line. So the first step is we're just going to write in the starting point and the ending point as the bounds. So the starting point is 0, and the ending point is r times 2 pi I over 3. Now we notice that if we let z equal x, where x is a real number, times e to the 2 pi I over 3, then x is going to go between 0 and r, right? So that this turns our integral through the complex plane, which is a bit nasty to evaluate, into an integral from 0 to infinity on the real axis, which is really nice. So once we substitute everything in, calculate our differential, which is e to the 2 pi I over 3, we get that our integral is equal to e to the 2 pi I over 3 times the integral from 0 to infinity of 1 over x cubed plus 1 dx. And that x cubed plus 1 just happens because e to the 2 pi I over 3 cubed is just 1. So that's a quick little example here. I have one more example because this is a little bit of a tough topic. So in this situation, our straight line does not start at the origin. So example number 2, we have f of z equals natural log of 1 minus iz over z squared plus a squared. Now, this line goes from z equals I plus epsilon to z equals I r plus epsilon. And of course, we're taking r goes to infinity and epsilon goes to 0. So this is a visualization of the line here. It's not a very good example because I didn't fill in everything, but essentially we're talking about something that's just infinitesimally to the right of the imaginary axis, and it runs up from I to I infinity. So, of course, the thing we're going to do, as we did in the past ones, is we're going to write in the bounds. So I plus epsilon as the lower bound, and IR plus epsilon as the upper bound right here. Then we notice, see how these are, actually I'll give you guys a moment. You should try and figure out the substitution that you should make to turn this into a real axis integral by yourselves. Now if you were able to figure that out, you would have found that z equals ix plus epsilon, where x is going to go between 1 and r. And the reason we're making this substitution is, as you can see, we have I plus epsilon, IR plus epsilon. That's I times some number plus epsilon, where that number is real, right? So that's the substitution we're going to make. dz is going to be I dx, and then that allows us to go ahead and plug in everything right here. We get an integral from 1 to r, and then we let r go to infinity and epsilon go to 0, and we get I times the integral from 1 to infinity of ln 1 plus x over a squared minus x squared. Very nice. So now let's go ahead and look at some practice problems. So for these practice problems, you don't actually have to evaluate the integrals, you just have to represent the line integrals in terms of an integral over the real axis, remembering that r goes to infinity and epsilon goes to 0. So here are our 5 examples right here. Alright, hopefully you were able to figure out all those practice problems. Let's go ahead and move on to the next topic. Okay, now we're going to talk about small circle integrals. So small circle integrals are a little bit of an interesting topic. Usually we have small circle integrals when there's a certain point that we want to avoid in our integration, but it's sort of like in our way. So for example, this point may be a pole or it may be a branch point. And so essentially we'll have to integrate over the point, but again, we can't integrate over points like this. So So what we do is we imagine that we integrate in a small circle around the point, and then we take the radius of that circle, which we call epsilon, we let epsilon go to 0. And so that's essentially how we get small circle integrals, and the ways to evaluate them vary depending on the type of point that we're around. So for example, here I have a formula that helps us if our point is a first order pole. So if gamma is a positively oriented, remember positively oriented means going in the counterclockwise direction, circular sector of angle theta and radius epsilon, remember epsilon is going to 0, and f of z is analytic in the neighborhood of f of 0, meaning f of z doesn't have any poles near f of 0, and by near I mean like infinitesimally close, or branch points or branch cuts or anything like that, then the integral over gamma of f of z over z minus z0 dz is going to be I times theta times f of z0. And a way you can kind of internalize this is, you can imagine if we let theta equal 2 pi, then we're really going a full circle around that point z0, and so since we're going a full circle around, we're really just going to get 2 pi I times the residue at z0, which is just exactly this. If we plug in theta equals 2 pi, that's going to be just the residue at that point. And so if we go a certain percentage around that circle, we're going to accumulate a certain percentage of that residue. So that's where this comes from. This formula is not difficult to prove, so if you guys want to try and prove it, I definitely suggest it, but it's absolutely not something you need to do. So let's go over an example here. This is actually an example from one of my more recent videos. So our function here is e to the I pi z over z cubed plus 1 dz. And we're integrating in a small circle of radius epsilon around the point z equals -1. Notice that we're going in the clockwise direction, which is the positively oriented direction, and also our angle theta is going to be pi because we're going a perfect semicircle, so that's half a circle, right? Now, in order to find, clearly we're going to have a pole here, because if you plug in z equals -1, you get 0 on the bottom. So when we factor everything, we can get that f of z is going to be equal to e to the I pi z over z squared minus z plus 1. And then all we have to do is plug in our formula. So remember, it's going to be I times theta times f of z0. In this case, z0 is -1. So I times theta is just going to be I times pi, and f of z0 is going to be e to the -I pi all over 3. So overall, our answer is going to be -I pi over 3. And you can see that in one of my recent videos. However, sometimes we aren't actually going around a pole. Sometimes we're going around what's called a branch point. Now we'll get to branch points later in this video, and we'll cover them fully in the next video. However, this is not really, this is also an important topic, because we can never integrate over a branch point, so we always have to go around it. So that's probably the main reason why we're going to be using these small circle integrals. Now, almost always, these small circle integrals are going to go to 0 because, well, you'll see why. And the main way to do these is either you can use parametrization or you can use the estimation lemma. So in this case, I'm using the estimation lemma because it's a little bit more familiar to us. So in this case, we're going in a small circle in the counterclockwise direction around the point z equals 0. And we have ln z over z squared plus 1 dz. Now we're going to use the ML inequality, right? So m is going to be the maximum value of ln of epsilon e to the I theta over epsilon squared e to the 2 I theta plus 1, because any point on this curve right here can be represented by epsilon e to the I theta for some theta between 0 and pi. And then using the absolute value right here, again using the triangle inequality right here, we get 1 minus epsilon squared. We get that the it's going to be less than or equal to natural log of modulus of natural log of epsilon plus 2 pi. Actually, this doesn't even need to be 2 pi. This could be pi. Again, just using the triangle inequality on both the top and bottom. And then that means that ml, remember that L is going to be pi times epsilon, is going to be less than or equal to pi epsilon times the times the modulus of natural log of epsilon plus 2 pi. Again, this can just be pi. And on the bottom, this should be 1 minus epsilon squared, not epsilon squared minus 1. Don't worry about that. But anyway, as we take the limit as epsilon goes to 0, this epsilon on the top is just going to dominate over everything, and so it's just going to be equal to 0. So almost every situation, these integrals are just going to go to 0, so you don't really need to worry about it that much. But always just go ahead and do a quick check. It's always good to, just show this just to be sure, because if you make a mistake now, it might be hard to fix it later. So here's some practice. They're all going to be over the same place right here. So some of these are going to be, these are just different small circle integrals right here. Some of them might go to 0, some of them the theorem that we stated before. Anyway, go ahead and try them. You might have to use. Alright, so next topic is by far the toughest one, and it's going to be a little bit hard for me to explain it, but I'm going to try my best. So some functions like ln z and square root z are multi-valued, and what this means is depending on how we define natural log of z, or typically you'll write log of z, and square root z, or any fractional power of z, there's different ways that we could define it, and they could have different values at the same point. For example, for square root z, there's always two possible numbers which you could square in order to get z, right? So that's why square root z is a little bit tough to define. And at the same time, e to the 2 pi I equals 1, which causes problems with ln z, because if you think, okay, what's natural log of z, or natural log of 1? Well, you would just say 0, right? But I'm telling you e to the 2 pi I also equals 1, so natural log of 1 could also be 2 pi I. So that doesn't really make any sense, and again, using this fact, it could be 4 pi I, it could be 6 pi I, it could be 8 pi I, and stuff like that. And no matter what number you're taking the natural log of, you're going to have this problem because, again, e to the 2 pi I equals 1. So in order to fix this problem, what we do is we fix the argument. Now, the argument just means the angle, which you should probably know if you're on this video. We fix the argument of a complex number to an interval between some angle alpha and some angle alpha plus 2 pi. Most commonly, this means that our argument is going to be between negative pi and pi, but depending on the function in the contour, we may choose a different branch cut. So this is called a branch cut. We're going to define where our natural log is going to jump. So here's what I mean by that. So in this situation, we have theta equals 0 going to be right here. We're looking at the situation where negative pi is less than the argument of z, which is less than pi. So if we move in the counterclockwise direction, our angle is going to increase until it reaches pi. And if we go in the clockwise direction, our angle is going to decrease until we get to negative pi. But notice where these 2 points meet, the argument is not very well defined because, well, right below this line, our value is negative pi, and right above it, our value is pi. In fact, we completely jump over this line, right? The value changes by 2 pi when you cross this line. And since the argument is an important, it's part of the natural log, essentially. ln z is equal to the natural log of the modulus of z plus I times the argument of z. So this discontinuity that exists in the argument of z also exists in the natural log of z. And this is why the natural log of z is neither an analytic function nor a meromorphic function, because it will never be continuous over this entire line. So here's another example of a branch cut we may choose. 0 is less than the argument of z is less than 2 pi. Now in this situation, theta is going to increase going counterclockwise in a full circle, right? But again, when we reach this full circle, if we want to keep going, our argument is going to change by 2 pi. And another common branch cut that we might pick is negative pi over 2 is less than argument of z is less than 3 pi over 2, which means that our branch cut will run from z equals 0 all the way down to negative I infinity. So each branch cut is going to start at a branch point. Now the branch point is usually going to be z equals 0 for ln z and run out to infinity. Now, of course, if you have the function like ln z plus 1, then your branch point is going to be whatever makes the input of ln z 0. So it would be negative 1 in that case. When we move over the branch cut, the function's value changes suddenly, causing a discontinuity, so the function is not analytic in the region. I already discussed that. For that reason, we have to carefully place branch cuts so that they are outside of the contour, because otherwise we wouldn't be able to use the residue theorem. Here's another example here with square root of z. Now, when you take the square root of a function, its argument is halved, right? Just because of the way that exponents and powers work. However, when we say that we have the angle, what does that really mean? Well, if we define our argument of z between negative pi and pi, that means that everything, it's always going to move to the right? Because, our angle is pi over here, so it would go to pi over 2. It's always going to move this way. And when we're below the branch cut right here, it's always going to move this way. However, if we defined our branch cut somewhere else, like for example, if we defined our branch cut on the positive real axis, then a point right here would get mapped all the way back here when we take the square root, which is totally different behavior, which shows that the branch cut is incredibly important because it changes the behavior of square root z. Now, fractional powers also have branch cuts since calculating them requires dividing the angle, and this can get very, very hairy. So the way that we make this a little bit easier is we define z to the p when p is not an integer as e to the p ln z. So now these fractional powers are in terms of natural log of z, so we can just use the same branch cut for natural log and for fractional powers, right? Otherwise, we would have to deal with multiple branch cuts, which you guys will soon learn is very, very annoying. Oh, sorry about that. So there are two things to keep in mind when choosing a branch cut, and we'll talk about choosing a branch cut in the next video a little bit more. The first thing is that we need to make sure the branch cut lies outside of the contour, and that's pretty straightforward because if the branch cut is inside the contour, we can't use the residue theorem. The other thing that's a little bit tricky sometimes is to ensure that your function still evaluates to the original function. So an example of this is, let's say we wanted to integrate a function with natural log times some other function, right? So f of z equals natural log of z times g of z, where g of z is going to be a meromorphic function, so it's well behaved, but it has some poles. The branch point is going to be z equals 0, which I've marked on the graph here. We want to use this contour. It's going in the clockwise direction, and notice that this is our semicircular contour that we've used for pretty much everything, but the exception here is that we have this little indent in our contour. And this is going to be one of our small circle integrals, which I talked about further. So given that this small circle integral happens because of a natural log, based on what I've told you, do you think the small integral is going to have a value that it contributes to the integral, or do you think it's going to go to 0? Now, hopefully you were able to guess that it's going to go to 0 because small circle integrals with natural log almost always go to 0. Now, the trouble here is we have to pick a branch cut for natural log of z. And there are 4 options that I have detailed here. Let me zoom out a little bit. I want you guys to try and figure out which one we should use. Keep in mind these 2 rules right here. And remember that our original problem was evaluating an integral on the real axis of f of z. So let's go over each of the options one by one. So option A, 0 is less than or equal to the argument of z is less than 2 pi. Now in this situation, we have to look at, okay, where's our branch cut going to be? Well, our branch cut is going to be on the positive real axis right here. And the problem with that is that our contour integral actually goes right over the positive real axis. So that's no bueno. That's not good. Because then we won't be able to use the residue theorem, and we might get the wrong value for our integral. So let's look at option B. The most common choice of branch cut is going to be negative pi is less than argument of z is less than or equal to pi. However, this example doesn't work because our integral, again, goes over the negative real axis, which is exactly where the branch cut would be if this was our branch cut, because as you can see, right here would be the angle pi or the angle negative pi, so that's right where our branch cut is going to go. Now option C looks very nice, because if we look at where the angle 3 pi over 2 and 7 pi over 2 meet, that's right here on the negative imaginary axis, which is nice and far away from our contour, which means that we'll be able to use the residue theorem to evaluate the integral. However, notice that for C, this interval that we have right here does not include the argument of z being 0. And a fundamental assumption of the natural log is that the argument of, the natural log of a real number, a positive real number, is going to be also a real number. I mean, think about it. When you take natural log of any positive real number, you get a positive or negative real number out of that. You don't get an imaginary number. But if we define our argument with this definition, a real number would have an argument of, I guess it would have an argument of 2 pi, right? So that means that the natural log of 2 would be the real part of natural log of 2 plus 2 pi I, which doesn't really make any sense in the context of what is a natural log. So This is not a good option either. And that means that D is actually the branch cut that we want to use. Because it has the same, the branch cut is located in the same place. It's located from z equals 0 and it goes to z equals negative I infinity. The difference is that in this case, the definition of the natural log on the real axis, the positive real axis, stays the same as our usual definition, which means that our function still evaluates to the original function, which means that both of these criteria are met, so that means this is the right branch cut to pick. So we're not going to do any practice problems for this because we're going to go over this topic more in part 4. But yeah, so next video we're going to go over common contours. So we're also going to go over how to choose a contour, and symmetry, bounding, and branching. Those are basically methods of choosing a contour. We're going to talk about what functions are nice for contour integration. So when you get an integral problem, how to analyze, okay, is this going to be good for contour integration, or is it going to be, or am I going to have to use another method? And we're also going to go over how to modify a contour and choose a branch. So anyway, I hope you guys enjoyed the video and I hope you learned a lot. Remember, you can always join my Discord to ask me any questions you might have. If you watched through to the end, thank you so very much, because I know that this was a very, very long video. The first time I recorded this, it actually went to 40 minutes. I'm not sure how long it is this time, but I'll give it a check. And yeah, so thank you for watching. Stay tuned for part 4, and if you're watching this whole series, thank you very much, and I hope you learned something. Thanks, see you next time.